Some think tuples in Python can't be converted to JSON, but that's actually a misconception. They can be converted, but they do lose their original Python data type. See, tuples are immutable. They cannot be changed once created, meaning you can't modify or add elements, unlike a standard list, which is fully mutable. So what happens when we convert it to JSON? First, we'll import Python's built-in JSON module. It comes completely standard, so no pip install needed. Let's set up a tuple of coordinates here. Next, we'll execute the JSON dumps function, passing in the variable containing our tuple. Watch closely. This action converts it into a list format. See? To prove this, let's import it back. In JSON, this is recognized as an array type. Remember, a Python list becomes a JSON array. That is the official specification. Look right here. As we convert it back, we first dump the data, giving us JSON data. Then we load it back into Python using the loads function. Once again, calling the JSON module. Let's check the resulting data type. Running this, we get a list back. See, it's explicitly a list type. We've completely lost the context that this was originally a tuple. Let's scroll down to a robust solution for this exact problem. Look here. If we convert both a list and a tuple, JSON treats them both as arrays, mapping them straight to Python lists. But what if you explicitly want a tuple back? You can supply the type directly within your data structure. Here, we'll explicitly pass a key called type set to tuple and store our elements under value. Once executed, here is our structure. The type is tagged as tuple, and our data is kept right here. Currently, it's still inside an array. Now, let's convert it back smoothly. We will check if our metadata says it's a tuple. If it matches, we are going to reconstruct that value portion into an explicit Python tuple. Perfectly clean. Once the data loads into our variable, we target the dictionary and verify the type. The type key guides us right here, and if it equals tuple, we grab the corresponding value and cast it directly. We wrap it effortlessly using the built-in tuple constructor. Run the script, and boom, we successfully get a tuple class back. Printing the type confirms it has been fully restored to a tuple. This highlights an essential design choice in Python, how it handles and maps tuples straight into JSON arrays. When parsing that JSON back into Python code, it automatically reverts to a standard list structure. It won't turn back into a tuple alone, simply because the concept of a tuple doesn't exist in JSON. But by passing explicit metadata like we did here, defining both the type and the value, you can effortlessly reconstruct your native tuples down the line. Found this useful? Smash that like button and subscribe for more. Python cannot convert sets into JSON format. So sets is a data structure in Python. So sets basically allow no duplicates. They are unordered, so no duplicates are allowed in sets. They're automatically removed, so Python does not automatically convert them to a JSON format because there is no equivalent of a set in JSON. So you might think an array is a useful type to have for converting from set data type into JSON. But array is not the correct option because you lose a lot of information around the purpose of set. So by design, Python developers have not created anything for it. So look at this example. So we're going to try and convert it, and you can see because this is a set, we get an error. This error, the object type is not JSON format, so you cannot serialize this into a JSON. So how do you convert it then? Well, if you really want to convert it, then what you need is a wrapper. You need to convert this to a list or a tuple. So in order to do that, what you can do is you can either use list over here, and this is the list constructor. Just wrap it around your variable name. So this is the variable name that has the set in it. And we're going to convert it into a list by wrapping it around with a list. This is the list class name, which is by default it takes in a set and converts it into a list. So here you can see we converted it, and now we run and it has changed the data to JSON correctly, because when you read it back, you will need to convert it back into a set because otherwise Python will treat it as a list. And in JSON, this format, although it looks like a list, this is array in JSON while Python refers to it as a list. Because of these square brackets, the square brackets in JSON mean that it's array while in Python it means it's a list. By default, Python's JSON module effortlessly handles multiple data types, but there are a few limitations. It only supports specific data types, meet the dictionary. You can easily recognize a dictionary by its opening and closing curly braces. Inside, you will see a key separated from its corresponding value by a colon. plus a comma. That's one pair, key and value. Then you have the next pair, like department paired with engineering. This is the exact type of Python dictionary that the JSON module can convert into a clean string using the dumps function. Next, we have lists. A list always starts with a square bracket and ends with a square bracket. It works exactly like shopping lists. Here we have an example containing a laptop, a monitor, and a keyboard. Next up, we have the tuple. A tuple looks like a list, but it cannot be changed. Once you create it, adding new items is completely blocked. Imagine a variable holding two cities, like London and Paris. If you want to add New York to that collection later on, you simply cannot because its state is permanently locked. Lists can change. Python will convert both of these into JSON smoothly. But notice this detail. When we run this script, you will notice that the dictionary becomes a native JSON object. The list converts perfectly fine too. Perfectly. But look closely, the tuple is actually transformed into a standard JSON array type. This means both of these Python structures, the list and the tuple, map directly to an equivalent array format. They both end up as the exact same type. Because of this, we lose a bit of information, since Python tuples are inherently immutable. No, JSON cannot show that constraint. They are forced into the same array format, right here. When decoded back into Python, it returns as a standard list. Text converts too, like strings here. Numbers too, both integers and decimals. Look here. It converts cleanly. True, work as well. But notice this detail in Python. True begins with a capital letter T. JSON lowercases it. Same for false. It uses a capital letter F in your Python script, but converts to all lowercase in JSON. Even the Python none type converts directly into a null value within JSON. That is how they map. These are the primary data types you can convert. Mapped. Perfect. Done. Go. Of course, you can manually transform other data types first, and then store them inside your JSON. But natively, only these core structures are supported. You can definitely convert custom objects as well, but that requires custom code to manage. The formatting, the built-in dumps function inside the JSON module handles all of this automatically for you. By default, Python's JSON dumps function adds extra spaces to your output. Let's take a look at how this works in a live code example. First, we import Python's built-in JSON module. It is ready. Our dictionary. Now, let's pass our user variable into the JSON dumps function. Notice that the resulting output mirrors our original dictionary structure. We see the keys for name and role, but take a closer look at this JSON object. Pay attention to the spacing right after the colon. Between the key and its value, a blank space. Python automatically includes spaces after both commas and colons. When sending data over the web, these extra characters consume unnecessary bandwidth. To fix this, the dumps function offers a powerful separators argument. Let's inspect the function definition together. As we hover over the dumps configuration, you will see a list of customizable parameters. One of the most useful options is the separators setting. It expects a tuple. As a reminder, a tuple in Python is defined within round parentheses. Inside, we pass two specific strings. We will provide a comma and a colon. The comma separates items, while the colon separates keys from values. This maps directly. Let's double-check the official definition. If we look down at the separators documentation, it confirms how custom separators behave. We have the item separator right here. Next is the key separator. The item separator is a comma, and the key separator is a colon. Notice that the default configuration includes an implicit trailing space. If you leave it blank, Python will always insert those extra spaces. To achieve maximum optimization in a hyper-compact format, explicitly override them with a tight comma and colon. Let's apply this exact configuration to our code block. Running this now completely eliminates all white space from the string. Compare this to the default output, which heavily spaces out the items. That is the difference between an unoptimized string and a perfectly streamlined payload. For production-grade JSON optimization, always define your separators. Notice how changes don't break this. Spacing is fully controlled by Python. It handles formatting under the hood. If you found this optimization trick helpful for your Python projects, smash that like button, subscribe, and leave a comment below. Here is a powerful trick to optimize your JSON outputs in Python, sorting your data automatically. Take a look at this employee dictionary. It contains salary, department, and name. Right now, the keys are completely unordered. Sorting alphabetically means department comes first, followed by name and then salary. Why does this matter? Great question. Let's check the output before diving in. We have two examples here. The dumps function generates our JSON. It converts a Python dictionary instantly into valid JSON. Here is the raw unsorted output. Notice it keeps the original order: salary, department, name. But check out this second line of code. We set sort keys to true. This magic parameter sorts the keys, just the keys. Keys and values mapped cleanly. Everything gets organized. Alphabetically, department comes first, then name, and finally salary. Crucially, the values stay unchanged. Only the keys are sorted. Keep that distinction in mind. So why should you use this? Why put effort into sorting keys? It is perfect for testing. Tools like Git and file diff checkers expect both files to match line by line. If your keys are randomly ordered, you will get annoying mismatches. But sorting by keys guarantees identical structure every time. Whether you have department name or age, the layout stays predictable. This is a game-changing trick for your deployment pipeline. It simplifies diff comparisons in Git or any code review tool. If you're committing database seeds, test outputs, or logs, enabling sort keys ensures your team can easily track changes side by side without the clutter. And there you have it, perfectly ordered JSON data. If you found this sorting tip valuable and want more Python secrets, smash that like button, drop a comment, and subscribe for more epic tutorials. In Python, you can unlock the power of regular expressions simply by importing the RE module. This built-in module gives you instant access to a massive range of pattern matching tools. Best of all, there's absolutely no need for external pip installations. It comes completely standard with Python. Once imported, let's look at our data. We have a raw text block containing multiple order numbers. This information is mixed into standard text format, waiting to be extracted. Imagine you just pulled this messy data from an external system, and now you need to isolate every order number directly into a list. To do this, notice the consistent pattern. Each ID starts with a hashtag, followed by the specific order digits and then the word shipped. Crucially, each target sequence is cleanly isolated by a standard space character, meaning there are no extra characters clinging to the end. There are no trailing digits here, for instance. It is not concatenated directly to a timestamp. If an order looked like this, followed immediately by a date like 2026, followed by 0617, our current logic would need an adjustment. Our current goal is simple: capture and extract only the essential order numbers. To do this, we use the highly efficient findAll function from the RE module. All we need to do is pass it a clean, raw string pattern. Inside the pattern, we type a backslash followed by the letter D, which tells Python we are explicitly hunting for numeric digits. Adding a plus symbol means we want to grab the full continuous number rather than just a single digit. By including that plus sign, Python bundles all connected digits together beautifully in one seamless sequence, ready to be stored neatly inside a list. Let's run this code and see the magic in action. Look at that. It instantly extracted order numbers like 7821. Every single one is captured. Watch what happens if we append a space followed by a year like 2026. As you can see, the expression isolates 2026 as a completely separate match. Now, what if we make a mistake and completely leave out that crucial plus symbol? Currently, our clean grouping works perfectly, but the moment you remove the plus operator, it shatters the sequence into individual, isolated digits. You get 7, 8, 2, 1 separately. See right there? And the next order turns into 9, 9, 1, 2. We don't want that. Instead, we need them unified as a clean group. One uninterrupted block for each distinct order number, and there you have it. The boundary between matches is defined by any non-digit character. A space acts as that boundary, telling Python exactly where to slice the text, which is precisely why our output looks incredibly clean on the screen. If we check the object type, notice that the return value of this function is a fully standard Python list. This list is stored in a variable, enabling you to manipulate it, using all your favorite native Python list operations. Regular expressions are absolutely vital, especially in the world of AI. Mastering them is key to becoming a top-tier professional. Let's dive into a quick example. Python comes with built-in regular expression support. We use the RE module, which stands for regular expressions. It's standard, so no pip installs are needed. Take a look. We have this text, John Smith James. This is the target string we want to search. Our goal is to extract the full name exactly as it appears, while also capturing each individual part, John Smith and James. To demonstrate, I've set up a simple script. Notice that this variable will return a match data type. This specific object is returned by the search function, providing information built right into the module. Take note of the RE references here and here. This match object is your key to accessing all the data. You can use the dot group syntax and supply an index like 0, 1, or 2. Let's run this to see it in action. And yes, this error is by design. It's the perfect way to show how this works. Right now, we aren't using any capture groups. Index 0 successfully returns, but notice the underline showing an error. It cannot find index 1, even though index 0 works. Let's see what printed out at index 0. It outputted John Smith. Why? Because our search pattern requires a standard backslash. You must always include this backslash. This defines the pattern we want to match. A word plus a space character, followed by another word. We want to capture that specific sequence. By design, group 0 always returns the entire match. So when we search for a word, a space, and another word, group 0 is that. To get individual parts, we wrap them in round parentheses. Let's run this updated version. Look at what happens now. We still have group 0, and the error is gone. Group 0 captures the full matched string. That includes a word, a space, and another word, John Smith. Now look at group 1. This first segment is group 1, John. Group 2 isolates Smith right here. Wondering why it missed James? Because our pattern is only matching 2 elements. To extract a third, we need to search for that third word. Let's add another space character. Now we track 3 groups. When I execute this, group 0 expands to hold the entire match. A word, a space, a word, a space, and a word. There it is. This always holds true. Group 0 always exists. Look at John Smith over here. That represents position 1, so we have group 1 and group 2. Group 3 isn't visible because we haven't printed it yet. Let's simply reference group 3 here. And now we successfully capture James. That's how capture groups operate. These round parentheses are your capture groups, defining subsets beyond group 0. Keep watching to master regular expressions. Let's level up our knowledge of regular expressions. This simple example will build a powerful foundation for your coding. Looking at our code here, we import the regular expression module. It's built right into Python and goes by the name RE. No extra installation required. Forget about pip install. Next, we use the findAll function. This powerful tool scans the string for specific patterns of characters. For this match, we will use a backslash, followed by a lowercase d. The D stands for digit, but notice the massive difference between a plus operator and an asterisk star operator. Take a look at our target string, A, B, C, D, 1, 2, 3, X, Y, Z. To isolate just the numeric digits, we tell Python to scan for numbers. The plus sign means 1 or more. This is crucial. 1 or more. Starting at 1, minimum of 1, but the asterisk star means 0 or more. Notice that 0, not 1. 0 is the magic number here. Let's execute this script right now and observe the fascinating results. The plus operator extracts 1, 2, 3 cleanly. But run the asterisk code and wait, what is going on here? This looks bizarre. It captured 1, 2, 3, but it also returned all these empty strings. Why? Because the asterisk matches 0 or more digits. Or more. It checks the first character A. It's a letter, not a digit. So, since backslash D looks for digits, and the asterisk allows for 0 matches, Python says, no digits here, that's a valid match of 0 digits. Empty string. Next B, another empty string. See? Another empty string. But then it hits the number 1. Boom, a digit. It locks it in. It keeps scanning. Number 2, yes. Number 3, digit. It groups them together. Keep going. But right after 3, the digits suddenly stop. It saves 1, 2, 3 as a chunk. Then it moves to X. 0 digits found. So another empty string. Same for I and Z, both yield empty strings. And notice that final empty string at the very end. But why? Python checks the position right after the Z. Since nothing is there, it triggers one last empty string match. Keep this in mind when working with the asterisk. See the stark difference between them? The plus operator gives you purely the targeted digits, while the asterisk floods your results with empty strings from the surrounding characters. Depending on your goal, both operators offer incredibly powerful ways to parse text. Master this distinction and you'll unlock the true potential of regex. Remember, the plus operator requires a minimum of 1 match, while the asterisk happily accepts 0. And that's the secret. Let's extract this invoice number using regular expressions in Python. We import the built-in re module. Built into Python, no extra setup needed. It comes completely standard. Look at our target string. Imagine we have this input text, an INV prefix followed by a dash and a unique ID. Our ultimate goal is to isolate and extract just the digits. Ignoring the INV prefix, watch, will trigger the power of the research function. This scans for our pattern. It returns a match object, allowing us to access specific capture groups. Our structure. Invoice numbers share a fixed format. The literal letters INV, a dash, and trailing digits. Let's test this layout. Right now, it's matching a static sequence. It returns INV and the dash, but we need to make this fully dynamic. Hard-coding numbers won't work because invoice digits change constantly. It's 1, 2, 3, 4, 5, but next time it could be any random numerical sequence. Explicit values just won't cut it. Instead, we employ a powerful regex special sequence. We use a backslash followed by a character, specifically targeting numeric digits. That's a lowercase d. Note, this is standard regex. Lowercase d instructs Python to search for any digit. Let's execute this and look at the resulting match. We capture the INV prefix, but only, wait, if we just chain another d, it breaks? That's a classic syntax error. Regex works differently. We need a quantifier to say 1 or more digits. For this, we append the plus sign modifier. Check out this beautiful output. It's dynamic now. It automatically captures numerical strings of any length. Even here, it grabs them. This is fantastic progress. But how do we isolate just the numbers and ditch the INV label? We could clean the text using Python string methods, but the most elegant solution is right here in regex. Wrap parentheses directly around our digit pattern. This forms a group. Note that the dash stays outside, matching INV, our exact format. Outwardly, the terminal output looks completely identical. But behind the scenes, Python isolates the parenthesized part into a new index. Let's update our print statement to target index 1 instead of 0. Target index 1, group isolated. Index 0 is the full match, all of it. But position 1 holds our clean, isolated group. Look at that. The numbers are perfectly extracted, completely separate from the prefix. Now for an advanced trick. We can place parentheses around the prefix as well. Watch how the data shifts inside our capture groups. INV dash is now captured, but we want to ignore it. To prevent storing that prefix, add a question mark and a colon into the group. See what magic just happened? It cleanly isolates our core numbers. Before adding the colon syntax, it stored INV as its own distinct capture. This pushed our actual target digits into a third index. We had INV in group 1 and the numbers in group 2. Remember, index 0 always retains the entire matched string. No matter what pattern you write, index 0 grabs the full match. From there, group 2 isolates the exact numerical digits, while group 1 holds the prefix.